Section: Introduction. In this section, we explore programming by example, PBE, systems, which tackle the task of constructing source code for a hidden algorithm based on input-output examples. PBE is crucial in the field of artificial intelligence and differs from recent work on code generation using large language models, LLMs. Instead of generating code from natural language, PBE focuses on few-shot inductive inference, where the goal is to infer a program that generalizes to new inputs without relying on natural language cues. We investigate whether LLMs pre-trained on source code can effectively solve PBE. If successful, this would enable PBE in general-purpose languages like Python, expanding its capabilities beyond domain-specific languages. Failure of LLMs in PBE tasks would indicate a lack of inductive reasoning and over-reliance on natural language cues for code generation. Our findings suggest that pre-trained and instruction-tuned models are not efficient for PBE tasks, aligning with recent research. However, through fine-tuning, LLMs can achieve higher performance in PBE, especially when not required to generalize extensively beyond the fine-tuning data. To address the generalization challenge, we propose an algorithm to adapt LLMs to small and labeled problem datasets, reducing the domain gap. By following this approach, we enable PBE across Turing-complete languages in various domains, such as algorithms on number vectors, string manipulation macros, and graphics programs. Our final models outperform custom symbolic search algorithms and even surpass powerful closed-source models like GPT-4. Additionally, our system can tackle a wider range of problems compared to traditional symbolic methods, thanks to the flexibility of Turing-complete languages. Programming by example involves synthesizing a program row that maps inputs X to outputs Y. The program is expected to precisely match the given examples, where the language L typically represents a domain-specific language tailored for the PBE system. For instance, systems like FlashFill generate string manipulation macros for spreadsheet tasks using a domain-specific language that includes regular expressions, string operations, and limited loop functionalities. PBE systems aim to generalize to new test cases beyond the provided examples. While basic PBE can involve exhaustive search for a consistent program, practical systems rely on carefully designed domain-specific languages to guide the search efficiently. These languages encode symbolic knowledge to focus on promising programs but may limit the expressiveness compared to general-purpose languages. In addition to traditional PBE tasks, such systems can also handle sequence extrapolation and data compression scenarios. A comprehensive solution to PBE that can express solutions in general-purpose languages would be highly beneficial for various inductive inference problems. Recent successes of LLMs in solving programming problems highlight their potential, although challenges remain in applying them to PBE tasks effectively. Section Summary. In this section, we explore the potential of large language models, LLMs, pre-trained on source code to solve programming by example, PBE, tasks. We find that while pre-trained and instruction-tuned models perform poorly in PBE, fine-tuning LLMs can significantly improve their performance within a limited domain. By adapting LLMs to small and labeled datasets, we bridge the gap in generalization, enabling PBE over Turing-complete languages like Python, expanding the scope and effectiveness of this paradigm beyond domain-specific languages. Section: Methods. In this section, we explain how we perform programming by example, PBE, using basic prompting and fine-tuning with a pre-trained model. Basic prompting involves constructing a prompt from input-output examples and generating programs that satisfy these examples. Fine-tuning enhances this approach by training the model to predict programs from input-output pairs in a dataset. However, obtaining a dataset with program examples and corresponding input-output pairs is challenging, especially for new applications like graphics programs. To address this data scarcity, we start with a small manually created dataset and use it to prompt the model to generate new programs and inputs. The output from running these programs on the inputs forms a new dataset used to train the model further. This fine-tuned model learns to perform probabilistic inference in a graphical model. We refer to this fine-tuned model as Q_theta, rho vert x, y. Our method is similar to self-instruct and wake-sleep techniques but with some differences. We use prompting to expand the dataset and train an inference network using samples from a generative model. We do not retrain the generative model itself. Updating the generative model could be crucial when deploying the system on new types of problems. Adaptation is another important aspect where we aim to solve problems outside the distribution of the fine-tuning data. By iterating between pre-training with the seed dataset and testing on a new dataset without labeled solutions, we can adapt the model to new problem distributions. This iterative process helps the model solve more out-of-distribution problems over time. In our experiments, we explore different approaches to programming by examples in 3 domains: list functions, text editing, and logo, turtle graphics. These domains involve tasks like transforming lists of numbers, editing text, and generating images. We use various datasets to evaluate the performance of our models across these domains. Section Summary. In this section, we describe the methods used for programming by examples, PBE, with pre-trained models. Basic prompting involves constructing prompts from input-output examples and generating programs, while fine-tuning the language model, LM, improves this approach by predicting programs from input-outputs. To address the lack of datasets for new PBE applications like graphics programs, we create a dataset by prompting the LM with a seed dataset and running the generated programs to obtain outputs. This fine-tuned LM, denoted as Q_theta, rho vert x, y, learns probabilistic inference and can be adapted to out-of-distribution problems by iterating between pre-training with a seed dataset and testing on unlabeled data. This adaptation process aims to solve new problems and improve the generative model's performance. Section: How well does the fine-tuned model perform? In this section, we prepare seed datasets for different domains, create a large training set, and fine-tune a DeepSeek Coder LLM that was pre-trained on source code. For list functions, we start with 50 problems from Rule et al. 2024. For text editing, we consider using either SciGus or a 40-problem subset of prose. For logo, we begin with 200 training set problems. The fine-tuned models perform remarkably well in their respective PBE domains. Our fine-tuned model excels in list functions, outperforming symbolic and neurosymbolic search methods, as well as GPT-4. It also solves all list-to-list benchmark problems from lambda squared. In text editing, it surpasses FlashFill and approaches FlashFill++. In logo, it solves 90% of the test set, outperforming other systems like Dreamcoder, Lilo, and Regal. Our model generates code solely from images, without using any language clues. Additionally, it can solve a wider range of problems due to its ability to generate Turing-complete code. However, there are some limitations to these results. The fine-tuned model rarely produces a correct program on the first attempt and requires multiple samples to compare against ground truth examples. This rejection process takes a few minutes per problem on our GPU. Despite this, compared to traditional program synthesizers, the number of proposed programs is relatively small. The model's performance also degrades when tested on different types of data than it was trained on. To understand what leads to success or failure of the fine-tuned model, we explore various hypotheses. We investigate if program size affects success, if description length under the prior influences success, or if description length under the approximate posterior is a predictor of success. We analyze the average compute budget needed to solve each problem and compare it with these variables. Our findings show that the description length under the approximate posterior is a better predictor of success than program size or description length under the prior. This suggests that the model pays attention to input-outputs rather than blindly guessing. Section Summary. In this section, we evaluate the performance of our fine-tuned model across different domains by preparing seed datasets, synthetically generating training sets, and fine-tuning a DeepSeek Coder LLM. Our model excels in list functions, text editing, and logo tasks, outperforming existing baselines and even solving 100% of list-to-list benchmark problems. Despite requiring multiple samples and showing degradation in out-of-distribution tests, our model showcases qualitative improvements in problem-solving capabilities, especially in generating Turing-complete code. Section: Out-of-distribution generalization. In this section, we explore out-of-distribution generalization. We start by discussing the advantage of classic symbolic PBE methods, which do not rely on statistical assumptions for test problems. Unlike neural networks that may struggle to generalize beyond their training data, classic methods can synthesize programs perfectly within their defined domains. To test the model's ability to generalize beyond its training distribution, we use train-test splits that go beyond the d_seed distribution. We conduct experiments where we seed with psi-gus problems and test on harder prose problems. For list functions, we seed with Rule et al. 2024 problems and test on Shi et al. 2023 problems, which contain unusual combinators. In the logo domain, we seed with short programs and test on longer ones. By using these splits, we evaluate the adaptation method's effectiveness in improving out-of-distribution generalization. Our findings show that there is a noticeable drop in performance when testing out of distribution. For instance, a model seeded with prose problems and tested on a different subset of prose achieves 76% accuracy, but this drops to 59% when seeded with psi-gus problems, which are simpler. The adaptation method helps narrow these domain gaps by enabling the model to solve more out-of-distribution problems, increasing performance by around 10% or more in all domains. To better understand the adaptation process, we visualize the problems solved before and after adaptation in the logo graphics domain. Before adaptation, only a few out-of-distribution problems are solvable with a significant search budget. Adaptation allows the system to quickly solve similar out-of-distribution problems in the future but does not enable generalization to very different problems. Expanding the compute budget at inference time or introducing stepping stone problems in the adaptation set could further improve adaptation success. In related work, automatic data generation with LLMs involves prompting an LLM to produce outputs used for later learning stages. We generate a dataset d_tune by prompting an LLM with d_seed, without recursively prompting the LLM with its own outputs. This approach combines LLM generations with program execution to create program outputs, offering a different mathematical interpretation for our data generator. Our work aligns with the tradition of learning to search for programs in PBE. We demonstrate that fine-tuned models effectively accelerate search in PBE, making it feasible over more expressive languages like Python. Traditional PBE methods involve symbolically searching for programs consistent with input-output examples using domain-specific programming languages designed to facilitate efficient search and generalize to new inputs. Section Summary. In this section, we explore out-of-distribution generalization in programming by examples, PBE. We investigate how neural networks struggle to generalize beyond their training data distribution compared to classic symbolic PBE methods that can synthesize programs perfectly within their domains. By conducting train-test splits that push models to generalize beyond their training data distribution, we observe non-trivial degradation in performance when testing out of distribution, but find that an adaptation method can significantly improve generalization by around 10% or more in all domains. Section: LLMs as inductive reasoners. In this section, we, as inductive reasoners, explore the use of large language models, LLMs, for inductive reasoning. Recent studies have shown the value of using LLMs to generate abstract hypotheses from specific examples and translating these hypotheses into programs. We aim to address whether LLMs can create programs suitable for programming by example, PBE, tasks. We discover that, after fine-tuning, LLMs can indeed generate programs for both traditional and unconventional PBE domains. To enhance an LLM's code generation capabilities, one approach is to enable it to debug its own code when initial attempts fail the provided test cases. While we did not delve into this strategy, simply regenerating a new program from scratch post-failure already outperformed previous methods. However, exploring self-debugging strategies further could advance the boundaries of PBE. When it comes to selecting the best program from a set of LLM-generated options, various techniques have been proposed. Our approach involves filtering programs based on examples. Integrating more advanced selection methods, like self-debugging, could complement our strategy. Our study has limitations. Using large neural networks for PBE may not be practical for everyday users performing tasks on personal devices. Deploying smaller neural networks and investigating network compression and distillation could address this issue. Understanding why our system succeeds or fails reveals that the posterior likelihood is a better predictor than program size or prior likelihood. However, determining the factors influencing the neural network's probability distribution over solutions remains challenging. Discussing the effectiveness of fine-tuned LLMs in PBE, we find them to outperform many existing neural and symbolic methods, even in unconventional domains like logo graphics. This success may stem from LLM's tendency to explore a wide range of possibilities, aiding in solution proposal. While performance may degrade on new problems, it remains manageable, allowing for adaptation. Although excelling on benchmarks is promising, true success in real-world applications requires more than high scores. AI systems, including neural networks, have trade-offs such as unpredictability and computational costs. Despite these considerations, tuning LLMs for PBE shows promise in expanding the range of solvable problems and domains. We extend our gratitude to Joshua Rule for data processing assistance and Yewin Pu for manuscript feedback. This research was supported by an NSF career grant, along with contributions from Google and Cisco.